In this video, we will write our first eBPF based application which detects a file deletion and prints the process ID and command which have removed that file. For doing that, first what we need to identify a trace point which we could use for this purpose. Let us see how. We'll use a utility called BPF trace to list down all the trace points which are currently available in our system. This printed down all the trace points which are available in our system. So what we need to do here is to identify which one we could use for our purpose. In Linux, the files are essentially get stored into a file system, and in file system there is a journal which is kept by the OS to keep track of the file changes and where is this file located in the device, etc. What we need to look essentially is that is there any trace point which are related to inode. So for that, maybe what we can do simply is that we can do this we can do this and then grab inode here. So you can see here there are many trace points which are associated with inode, so you have to do a little research here and identify which one should be it. So I done the research and this is the one which we should be using in this example. What it do is that, like, whenever a file get deleted, this particular trace point get triggered ext for free inode. Essentially the inode will get freed whenever a file get removed from the file system. So what we need to use is this particular trace point. This is how, more or less, how you identify a trace point which suits for your use case. Now I will give you a walkthrough on the code which I have already written. Let's go to my screen here. So I have this sample app folder here, and in that I have a filegon.c file and a main.go file and a readme.md which you have some instructions for you to get started with. So let's first look into the filegon.c, which is the eBPF instructions which are written in C. Let's go line by line. So the first line include common.h, where we are including the necessary header files which contains the data structures and the helper functions which are used in this particular program. So you can see certain data structures and some type definitions, then some macros, these functions, right? All these have been imported from this common.h. So let us see what is there in common.h. Common.h will be actually imported from this header folder. You can see that a lot of BPF related header files you can just copy, paste and use it as it is. But the only thing is that you have to generate this vmlinux.h file. So this, how to generate this vmlinux.h header file, I have explained in my previous video. Do check that out. So this file, what it contains is the data structures which are used in the current running kernel. So we might need to use that in our eBPF code to parse the data which are gathered when a trace point is triggered. Yeah, that's pretty much about all this header part. Let's go back here. Now that we have the struct data underscore t user defined data structure here, so this have two fields, one is PID and one is com. So PID is to hold the process ID. Listen, the objective for this application is to collect the process ID and the command which have deleted a file, right? So to store, in order to store those information, I have created a data structure here, and I called it with a name data underscore t. And then we are defining the ring buffer here. The ring buffer is a kind of map which is available in eBPF so that we can get the data back to the user space. So this data structure, in this format, we will be collecting data from the eBP in this eBPF code, and we are getting that out of the kernel space to user space using the ring buffer. So that is defined over here like this. Then we have this sec macro, and in this macro we are kind of annotating this function to attach this particular instructions to this trace point. Okay, so that all will handle internally, so this macro will deal with it. Yeah, this is how you have to mention the trace point, like this basically. So then we have the function here. So I have named this function trace I not free. You can name it however you want, for like even you're writing for your use case, of course. Trace I not free, this ext free I not. We would also need to understand which data structure, um, like when this trace point get triggered, the data will be passed in which format. We need to understand that, right? So in order to do that, to understand that, what we could do is just copy paste this trace point name and then go back to your vmlinux.h file, do control F, control V, then you will see the extv for free inode. You are seeing here 3 entries. So both are type definitions and uh, struct definition and G definitions, right? So here you will see the actual structure for the particular data structure. So trace event draw ext for free inode. This is what we should be using to receiving the data when the trace point get triggered. Here you have this information, a trace entry, then dev with the dev underscore t structure, I know with the I know underscore t structure, then uid, gid, blocks, mod, data. Yeah. So each of this, what is it? You can easily find that out in the kernel documentation. It is available in the internet. You can go and check that out. I'm not going to go deeper here, but let's skip to the next part. So basically, I showed you what are the different data fields available for this structure. So this is how the received data will look like when this trace point get triggered. Then here what I am doing is I am reserving a space for the data with this structure. Like this structure we have defined the field PID and command. So to hold that this much data, reserve some space in ring buffer. So that is what exactly this helper function do, BPF helper function do. And you see here this events is the events which we have defined here. It takes argument as address of the events ring buffer and the size of the data which needs to be folded in that ring buffer. Here we are just checking if data is null or not. If it is null, then we have to return it. We have to handle this case. Then we have we are storing PID in the data, like we are using this helper function BPF get current PID underscore TGID helper function to get the process ID of this process. Like when this trace point get executed, that means there is a process which is triggering an inode free event, right? So that process ID we can get easily with this particular helper function, and I am storing that to the PID field in data structure. Similarly, I'm getting the command which ran, the command name which have executed the file deletion, which is actually associated with this process. I'm storing that to command com field in data struct. Basically, that's it. We got the information what we needed, right? The process ID and the command name, we got it. So after we getting that information, what we need to do is we need to submit that info to the BPF ring buffer. So for that also we are using another BPF helper function called BPF underscore ring buff underscore submit, and we are just simply passing the data here. So then at the end we need to return it 0, and here also we need to mention the license of this eBPF code. Why? Because if this eBPF code is not compatible with the GPL license, essentially we won't be able to use this BPF ring buff or get current com or PID TGID. We won't be able to use a couple or more of the BPF helper functions. All of the BPF helper functions are written in GPL license. So if you want to use them in your code, you have to make your eBPF code GPL license as well. So that is how it is right now. Maybe if you want to do something cross the source, I think then you might not be able to use any of the BPF helper function or certain functionalities which are available in the kernel, right? So in kernel also different things have different licensing. It would be a bit of an effort if you want to find out which licensing suits your needs or suits your application which is written in eBPF. So that's all about the C code here. Hope you understood all this. Now let's jump into our Go code here. Now let us take a look at the Go program which load and execute these eBPF instructions which are written in C. So here first I have some import statements. Apart from the basic ones, I have imported certain packages from Cilium eBPF module. And then I have a Go generative directive here which is commented out. So what it actually does is like when you run go generate main.go, what it will do, it will just execute this one. It will just do go run github.com/cilium eBPF cmd bpf to go. So basically this is a tool written by Cilium eBPF community. So what it does is it will take the filegon.c, the eBPF C instructions, compile them and create an object file which can be used by the Go program. And it also generate another Go program which include some functions and definitions for the object in the object file which is produced by this command. So basically the output of this command execution is one object file and a Go file. So that Go program, the functions which are defined in that particular Go file help us loading the object which is one of the output of this command, loading the object or operate with that object. All those functions will be there in that particular Go program generated by this command. So let us see that in action first, so that you will get more understanding of it. So you can see here there are three files, filegon.c, main.go, and one readme.md. Let us do go generate main.go. So now if I do this ls now, you can see that there are two new files. One is a Go program and one is an object file, as I mentioned. So this Go program, I cannot open the object file in VS Code, but I could open the Go program here. So this generated Go program will have certain functions like load BPF, then load BPF object, then the type definition for BPF objects, and all those functions are here which could operate on the object file, which will be embedded, like how it is going to load is like, so when you are running our main.go, or when we are running the eBPF application, how we would run is this, like go run star dot go. So it will also basically it will run main.go, then it will run this bpfel x86.go, and this file basically embed or load the object file as well with the go runtime when this program basically starts. So that's pretty much about it. I'm not running it now. Coming down here, so I have a data structure here. So this is exactly as same as in the filegon.c data structure. So this is the structure how we will be sending data to the ring buffer when the eBPF is running, right? So exactly the same data structure we need to define here, so that we should be able to read that from the ring buffer. So we have a process ID and command name of same type, unsigned integer 32 and character 16-byte character. So like as here. Okay, now in the main function where our program execution starts, so I have defined a channel, stopper channel here, and it is of type OS signal, and it's a buffered type channel. with the size 1. Whenever there is a signal or interrupt signal is happening, this function will get triggered and it will pass the voice interrupt to the stopper channel, and it do something, right? It will just pass the voice interrupt signal to this particular channel. So there should be somewhere else in this code where it is consuming this interrupt signal and exit from the main function. So why there is a need to exit from the main function is because you can see, like if I scroll a bit more, you can see that the incoming events, like the from the ring buffer we are reading the events in a go routine, and this is something which needs to continuously been done, right? Like whenever there is a deletion event, this go routine should catch it, and this will continuously run. This go routine is not blocking the main thread, it is an infinite for loop. So this go routine will not block the main thread, but this is an infinite for loop. But even though, since it is not blocking the main thread, there is a mechanism to block the main thread so that our application uh, is running. Like it should print the process ID and command ID whenever a file is getting deleted. So that is basically handled by this go routine here. In order to control the execution flow, we need to be running this program, and we need to exit the program when we press Ctrl C. That is the behavior we would like to implement, right? So that's why we have implemented a stopper here. So let me just cut this out so that you can see that in a single screen. So we have the stopper channel created here, and whenever we are hitting Ctrl C, it will be, that data will be loaded to save to the stopper channel, and whenever it receives it, it will stop the execution. It will go to the next line. Next line is the curly braces close here, and it will exit the main function. So if it is not receiving an interrupt, it will just wait here. It will simply just wait here for receiving an interrupt signal on the stopper channel. Whenever there's a value received, then it will just continue the execution to the next line, which is the exit of the main function, and it will exit the entire program. So now let me paste that back. Okay, so now let's go line by line from top to bottom here. I hope you understood the purpose for the stopper channel and how it help in interrupting the execution of this program. Okay, so now we have this block over here. What it do is we are trying to remove, we are using our limit module to remove memlock for this process. So what exactly it do is that Linux sometimes move the memory used by a process to the swap area, right? So we don't want to do that here. So in this eBPF programs, we need the data to be kept in memory. Whichever data used by this program, we need that to be kept in memory. We don't want that to be moved to a page in the swap area. In order to avoid that, we are doing this rlimit remove meblock here. Then we are loading the BPF objects. So these are functions which are taken from this particular file, which was generated by the go generate command. So what it will do, it will just create this objects variable. It will just load that object variable. BPF objects are nothing but program and map specifications. So those information will be contained in this objects variable. Then the next thing to do is that we need to attach to the trace point, and this is how we do it. Again, we are using this link module from Cilium eBPF for that. Then we are using trace point, and we are passing the trace point details over here. Here is ext4 free inode, and the objects in this objs, there's a function name called trace inode free. So basically this trace underscore inode underscore free later interpreted as this, like in camel notation. You can basically simply understand that this trace point, this subset of this trace point, like this is here ext4, and the name of the trace point ext4 underscore free underscore inode. So you can easily understand by just looking over your C program and seeing which trace point you have selected. So trace point slash, after the slash what is there is the subset of the trace points which are available in the system. So mention that subset name and the name of the trace point which you will be using in this program. So that you have to pass in the trace point function over here, which will attach this function to the trace point in the kernel. This is how we generally attach an eBPF code to a particular trace point. Next, what we are doing here is we are initializing the ring buffer. So objs.events. So events is the ring buffer name, right? So if you remember, events here is the ring buffer name, and we are creating a variables with that particular type. Then we are trying to read that particular ring buffer, like we are creating a ring buffer reader here. Ring buffer dot new reader is a function for that. Then we are passing the events, which ring buffer we need to read on, that details we pass here. And then basically this stuff, I didn't go through these steps earlier. This is basically error handling, like if we are receiving an error for that particular function call, and then how we need to handle it. And at the end, like you can see defer tp underling dot close and defer rd dot close. So what defer does is that when the program exits from the main function, if you are not closing it intentionally anywhere else, it will just closed by this defer statements. What we have done so far is that we have attached our function trace inode free to this trace point, and then what we have done here is we have initialized the ring buffer, right? And we initialized a new reader for that particular ring buffer, and that's all what we have done so far. The next thing is to handle the events. So we need to continuously read on that ring buffer and just print out the details if any such event happen. So that all are handled with a go routine here, and this is an infinite for loop you are seeing here. So this go routine will execute as another thread, so it is not it's really non-blocking. It won't block our main function. So if you want to do some other logics here, you can do that. This is very basic example for you to understand how you could write an eBPF application for your particular use case. Here this is an infinite for loop, and here this is how we are reading from the ring buffer. So this is a rd ring buffer reader which we have defined here. So rd dot read, then if there are errors, then it will return from this function. Essentially it will return from this go routine to the main function, and it will also print if there are some errors, otherwise it will just continue. Yeah, that is what this part is. We are trying to read from the ring buffer. Then here we are defining a variable of type data. Let me check. Yeah, data t, named data. Here we are reading with the bytes dot new reader. So basically from the ring buffer, it is coming as a stream of bytes. From this record record.raw sample, so basically it's a byte stream, and we are reading from we need to parse that with the data. So basically we have a structure defined here, PID and com. Each field have its own type. So what it will do, it will parse this bytes dot new reader. It will parse. It will just get that in the bytes format, and binary dot read will parse that data in byte array to this structure, this particular structure. So it will try to decode it, and if it is failing to decode it because of some maybe some type mismatch errors or something like that, then it will print an error like error decoding event, and it will just continue to accept the next event. Okay, lastly, we have two lines over here. These are basically to parse the data and print that to the terminal. The data, when I mean the data, it is the process ID and the command name which deleted that particular file. So here the data is data we are storing to data variable, right? And in data variable, we have two fields. One is com and one is PID. Com will contain the command name and PID will contain the process ID of that event which deleted the file. We are converting this byte array into string here, and then we are printing both PID and command name to the terminal. So that's it. That's all about this Go routine. So it is an infinite loop, as I mentioned before. It will just continuously read from the ring buffer. As the event receives it, it get printed on the screen. And whenever we press Ctrl C, this upper channel will receive an interrupt, receive one value. Whenever it receives a value, it will just continue to the next line for execution. It sees the closing curly braces and exit from the main function. So that's all on this Go program part. Now let us see this in action. Let me pull this app. Okay, sudo go run star.go. So one thing you have to notice here is you have to run with the sudo privileges, because the eBPF code requires sudo privileges to run in kernel, and then star.go, because I have all this code in main.go, but I am also using some of the functions which are available or provided by the generated Go file, and that generated Go file is the one which load the object file which contains the compiled instructions and map specifications for eBPF. So we have to run it like this. So let me run this. So it's not printing anything because there is no file get deleted or there is no not free event is happening. So let me try. I have created a test1.txt. So let's just remove it. It doesn't matter whatever data in that, test1.txt, and let's see here. So event received PID 65881 and command was rm. Using rm we deleted that particular file. Okay, that's all. That's all what I wanted to show. If you have any questions or comments, please mention that in the comment box. Thank you.